are looking at these objects. So I'm going to keep here the notation. S was the symmetric algebra of some vector space. And K is algebraically closed end of characteristic 0, just to avoid any kind of problems. And M was finitely generated, graded S module. That was the minimal resolution.
Characteristic P case, what happened?
Sorry?
Characteristic the base P is 0.
Yes.
If what happened if the P?
Well, it also works, but in some, just to take the shortcuts, at some point I want to divide by numbers. So I want to make sense to 1 over anything. So in general, many cases also work in characteristic P, but I'm mostly interested in characteristic 0. Anyway, funny things can happen in characteristic P, and Frank Schreier is a specialist in also in this area, and yeah, he can give you examples of so Green's conjecture, for example, fails in characteristic P. Green's conjecture.
Who is
Schreier.
Schreier?
Yes. He found counterexamples in characteristic P. Okay, so that's why I assume characteristic 0, because I don't want to say, well, this holds in any characteristic, this holds in characteristic 0 only. Okay, and we saw the last 2 days ago that these Betti numbers can be computed by Koszul cohomology. So we have this Koszul complex. And the cohomology at the middle, cohomology here is KPQ MV. And these Betti numbers, BP, P plus Q of M, are actually dimensions of KPQ MV. And just one convention. So if sometimes I will prefer writing KPQ of M instead of KPQ MV, or KPQ of X if X is in Pn. Sometimes, only sometimes. Sometimes. This stands for KPQ S, X, and V. So if it's implicit, then I will just omit V. But we have to be careful because, for example, if we take just a part of variables which span a subvector space, we still have M will have by base change will have also a structure over the smaller polynomial ring with different Koszul cohomology, although it's the same module.
Is it still finite generated if with the small?
Yes, yeah.
Finite generated grade S prime module. Something if it's smaller than it's infinite.
Yes, I don't know. Yes.
Yeah.
We will. Yeah, we should think about it. Yeah. Okay. So this presenting presenting Betty numbers as Kozulko homology actually has some advantages, because we can apply just one example of application is that we can apply all the machinery of homological algebra. And if we have this sequence M2, M3 to 0 of, so this is sequence. Actually, I should say that this holds true even if the module is not finitely generated. So this is true for any module. Yeah. So this can be defined in general. So this is, if this is a sequence of graded S modules, then we have an induced sequence, KPQ M1V, KPQ M2V, KPQ M3V, then KP minus 1, Q plus 1, M1V, and so on. So this kind of stuff. So we have plenty of, there are many samples in Green's original paper from 84. Which might, so these facts maybe are not that obvious if we work directly with minimal resolutions. Anyway, the basic question is basic question in syzygy theory is the following. What kind of information do Betty numbers beta PQ of some x contain? So I either look at the Betty numbers of the homogeneous coordinate ring, or something related, for example, the integral closure, or something which is very close to that. So all the problems in the syzygy theory turn around this question, or this type of questions. Let me just mention one fact, which is proved in Eisenbach's book, a theorem. Castelnuovo-Mumford regularity can be read of Kozulko homology. So the maximum of j minus I, such that there is beta ij different from 0, is the regularity of X. So that tells, so the regularity is a measure of the size of an ideal sheaf. But this is also a measure of the size of the Betty table. So that tells that the number of columns should be of the number of rows that contain non-zero elements should be the regularity. So after the regularity, everything will vanish. And this points to, classical regularity problems, and so on. There are actually plenty of interactions with geometry. One of them is the famous Green's conjecture, which I'll talk about the next week. Today I would the topic of today's talk is about syzygy schemes. It's that is this is a machinery invented by Green and Schreier and Schreier students that allow producing geometry out of non-zero syzygies. So the idea is to produce geometric objects out of non-zero syzygies. And this is quite interesting. Let me begin just by giving you an example. So this is a toy example. 7 points in P3. Then we will see how this example generalizes. Okay. It is so. It's well known that 6. We will consider X a set of 7 points in P3, which are in linearly general position. It's well known that 6 points in P3 always lie on in linearly general position, lie on a twisted cubic. For 7 points, it's not true. But there is something interesting happening with these points and twisted cubics. And the result is the following. The Betty table of X is one of the following. So there are two possibilities. So either 1, 3, 2, 3, 6, 3, or 1, 3, 1, 6, 3. And these cases are characterized by the following property. According to whether or not the points lie on a twisted cubic. So again, the Hilbert function is the same, like for 4 points in P2, but there is a difference in the Betty table, and the difference is given by whether or not this can be put on a twisted cubic. And we remark, if we look at the upper part of this Betty table, this is the Betty table of a twisted cubic, which we have discussed the last. We will see that this is that's not a coincidence. This is not a coincidence because let me just point out the following fact, and maybe we give a short proof of that. So if y is in Z, then beta I plus 1 of Z is lower than or equal to beta I plus 1 of Y. So if we look at the first row, the inclusion will so beta I plus 1 is the first row according to the rule of how do we put these Betty numbers in the table. Betty numbers are reversed. That's why we will get something. So this makes sense. So what I'm trying to say is that in this case, the points cannot lie on a twisted cubic, because if they lie on a twisted cubic, we should have something bigger than or equal to 3 here and bigger than or equal to 2, according to this rule.
What is y and t? I'm sorry.
Yes?
Y and t is what?
Any y and any z. Two varieties in the projective space.
Two varieties.
Yes, yeah. So that's a general rule, whether there are points, curves, or whatever. Each time we have an inclusion, if we look at the first, the linear strand of the resolution, the bigger the variety is, the smaller the Betty numbers are.
The first is I plus 1. Just
yes, just the first ones.
So here, where is the I plus 1?
Well, this is a general Betty table for an M. For a variety, the Betty table always begins by, at least for non-degenerate.
Yes.
I should have said that this is not degenerate. Yes. It always starts with 1. So here we have 0, 0. And then here we have the number of quadrics. And then relations between quadrics and so on. So this is the first strand, the linear strand, the strand of the quadrics.
If there is no quadric, then what?
So this is, if there is no quadric, then this is 0. Everything will be 0 because we don't have relations between something which is 0. So if there are no quadrics, then the whole linear strand is 0.
It's beta 1, 2. Beta 1, 2 is...
Yeah, so this is beta, let's write, yes. This beta 1, 2, beta 2, 3, and so on.
Quadric is...
Beta 1, 2, yes.
Quadric, number of quadric and their physics is preserved.
Well, or it can,
Yes.
so we have an inequality. But in this case, it's preserved.
Yeah.
And I will try to explain this phenomenon. Actually, why do we have this inequality? Because if y is in z, how do we compute? So beta I plus 1 is the dimension of ki1. This is of z, and the same with y. So we should prove that we have an inclusion. So we actually have an inclusion of ki1 of z in ki1 of y. And why do we have this? Because how do we compute this thing? So here we have wedge I of v, tensor v, because these varieties are non-degenerate. This comes from wedge I plus 1 of v. Here we have equality. And then the difference is at the wedge I minus 1 v, wedge I minus 1 v, tensor S2. And now let's see. So I2 of y is bigger than I2 of z. Then S2 of y will be a quotient of S2 of z. And then the kernel of this map, which computes Koszul homology of y, is bigger than the kernel of this map. then this means that this group is bigger than this one. And that's it. That's the explanation. If we want to look at the others, it becomes trickier, because we start to compare what happens with the. So it's not clear with the other strands. But for the linear strand, we only use the fact that this is S1. They are non-degenerate. This is the only thing we use. Okay. So we have so the standard formula for relating the Hilbert function and the Betti numbers, the one which I kept here on the blackboard, shows that we always must have 3 quadrics in the ideal, because it's just B2. So B2 will be this one minus this one plus this one, and B2 will be B1 is 0 and B0 is 1. So we just write that formula, knowing that HM of X of 2 is 7 already, and we get exactly 3 quadrics in the ideal. So we always must have 3 quadrics. So beta 1, 2 is 3 in any case. And now we have to. So if the next one, beta 2, 3 is 0. So if beta 2, 3 is 0, then we can apply once again the formula, and we get 1 cubic. You see, so we just continue on the diagonal one by one. We have 1 cubic, and then we compute this one, and we get 6, and this one we get 3, and then we stop. So if beta 2, 3 is 0, then then the Betti table looks like in the second case.
So beta 1, 2, 3 comes from this table or just that formula?
So the Betti table we don't know. So the Betti table will be like beta 1, 2.
Yes.
Then here we have beta 1, 3, beta 2, 3, beta 2, 4, and so on.
Yeah.
It will stop here because of the regularity.
Yes.
So we only have 2 rows. Now this is so the alternating sum of this one is B1, but this is 0.
Why B1 is 0?
Because we have 0 here and 0 here.
Yes. B1 equal to 0.
B1 is always 0. Now the B2 is the alternating sum of these things. But this is minus B1, 2. B2. So if and B0 is 1. So if we introduce there in the formula, HM of X of 2 will be, no, sorry, B2 will be 7 minus B1 is 0, B0 is 1, and then we have N is 3, J is 2, K is 0, and sorry, is it, maybe there is something wrong in that formula.
What is N?
N
is B.
N is 3.
B2. J.
N plus Is this formula correct? Let me. N plus j minus n plus j minus k.
N plus j minus k.
Yes, n plus j minus k. Yes, because j is this one. The sum is over k. So I got confused with this. The summation here is over k, and here is over j. So it's 3. Sorry, let's start all over again. So j is plus 2, and k is 0. Choose 2. So this is 5 choose 2. 5 choose 2 is 10. So this is 7 minus 10. This is minus 3. And it's fine, because it's minus beta 1, 2.
Yeah. Thank you.
Okay. So we have 3 quadrics, and we always have cubics. Just a side remark. Beta 1, 3 is different from 0. Why? Because if we take the multiplication, tensor v to I3 of x, this is of dimension 3, this is of dimension 4, and this is of dimension 13. So we always have cubics that don't come from quadrics. We have at least one cubic. Yes, this is 13 because it's 20 the number of cubics on P3 minus 7. They impose independent conditions on cubics. So we have at least 1. And actually in this case we have precisely 1. So this deals with the second case. So everything is played here, whether or not this beta 2, 3 is 0 or not. So if it's 0, then it's fine. And it's clear that in this case, the points cannot lie on a twisted cubic because of that this property. So now assume beta 2, 3 is different from 0. And then we will get a twisted cubic out of this information. And this is a pattern for producing syzygy varieties. Because here it's exactly, the general situation is of course much more complicated. But the principle is the same. We assume that we have non-zero syzygies and we produce a geometric object, which in this case is a twisted cubic. Okay, let's do that. So if beta 2, 3 is different from 0, then we have a linear relation among the generators of I2. Probably I should keep this here and maybe erase this blackboard. Okay. Then we have these 3 quadrics Q1, Q2, Q3 in I2 of x. And we have a linear relation. So now up to a change of coordinates, we can assume that we have this relation. So can assume x1 q1 plus x2 q2 plus x3 q3 equals 0. Now, so we have 3 quadrics with this relation, and now since the Koszul complex is exact on P3, so this is so the 3 quadrics will give an element in the kernel wedge, let me see. So actually we get out of this, and then I explain. 3 linear forms, L1, L2, L3, such that Q1, Q2, Q3 are the 2 by 2 minors of the matrix X1, X2, X3, L1, L2, L3. This is because we have an element in V tensor I2 of X, no, I don't want to go to the ideal. I want to see it as simply on the projective space. Yes. So this is an element in V tensor S2 of V that maps to 0 to S3 of V. But then here we have wedge 2 of V tensor V. So the causal complex on P3 is exact. So this is exact here. So an element of the kernel will come from the image. And that's because of this wedge 2 and of V, which will give X1, X2, X3, we get the minors. So wedge 2 here stands for the minors. So if we just write carefully this fact that the combination which we obtain comes from here, we get exactly what this claim. Okay.
So what's the 3 linear forms L1, L2, L3 such that Q1, Q2, Q3 are
2 by 2 minors.
2 by 2 minors.
Yeah, of this matrix. Yeah, we have to write down that. So we know that X1 tensor Q1 plus X2 tensor Q2 plus X3 tensor Q3. This is delta of some element from here. And that's how we get these minors. To be completely precise, I should have taken, but there are some technical details which I don't want to enter. I should take instead of V here just the span of X1, X2, X3, and say that here we have wedge 2 of that span. That's the right way to do it. And then we get these linear forms, which will be in this part. So this is what we get from this part.
Actually, I don't understand what the word. There exist 3 linear forms L1, L2, L3
such that these Q1, Q2, Q3 are the 2 by 2 minors of this matrix, of the matrix. So this means that Q1 will be, for example,
the minor of that one.
That one. Q2 will be of this one with the minus, well, up to a sign. And Q3 will be the minor of this one. This is the meaning.
So there is L1, L2, L3.
Yes, yes. There is. Sorry.
Yeah,
yes.
That's what I'm.
Okay. Yeah. Sorry.
So,
yeah. There are 3 linear forms.
I see.
Okay. Okay, and now the two rows here are independent and give the relations between the two quadrics. So let's note that the two rows generate the relations between the quadrics. Well, they give relations. Well, the first one is what we started from, but also L1, L2, L3 will give relations, because if we replicate this row here and we apply determinant to 0, we get, and we expand by the first row, we get new relations. And these generate all the relations, because if we had another linear relation here, then if we put on the first row, the determinant will be 0, just by definition. So the first row will be a combination of the second and the third row. Okay, so this shows that beta to 3 is actually 2. So as claimed here. And now there is an argument which I will skip. It's explained here in the book of Eisenbad, that these three quadrics define an irreducible curve. Hence, it must be a twisted cubic. So one should prove that this the ideal is we have a prime ideal. Okay, so and that's how we get the twisted cubic. We started from relations, and we got the twisted cubic. But let's analyze a little bit more. So we finished the proof, but let's look closer. So we had the hypothesis k21 of x is different from 0, and then we obtained out of this hypothesis our twisted cubic. But here we worked actually with an element in the kernel, which we saw is the same thing, is the kernel of the map from it was the same thing in the proof. The kernel of the map between the multiplication map between v and I2 of x to I3 of x. Why is this true in general? So this is a general phenomenon. Remark. So if we look at kp1 of x, this is always the kernel of the map, of the multiplication map, from which p minus 1 of v tensor I2 of x to wedge p minus 2 of v tensor I3 of x. And why is it so? Because we have this exact sequence, Ix to S to Sx to 0. And then we apply the exact sequence, the long exact sequence associated with this short exact sequence. And we obtain kp1 of SV. This must be 0 because it's the Koszul complex on the projective space. And we saw that it's exact. kp1 of x, kp minus 1, 2 of Ix, and then kp minus 1, 2 of SV. This is again 0. So we have an isomorphism, and if we look at the kp minus 1, 2 of Ix, how it's defined. So we have here wedge P minus 1 of V, tensor I2 of X, goes to wedge P minus 2 V, tensor I3 of X, and it comes from wedge P of V, tensor I1 of X, which must be 0 if the variety is non-degenerate. So this is the kernel of this map is actually Kp minus 2 of the ideal.
Why Kp1 is V equal to 0?
On the projective space, the causal complex is exact because it's the causal complex which we started from.
I see.
And all the KPQs
Kpq as V equal to 0.
of Pn are all 0 except for P and Q 0, 0. This is the only case where this is different from 0. And this easy trick actually allows playing with, like in this situation, going to the ideal. So a non-zero syzygy actually is a collection of quadrics. If we interpret this space by this kernel, is a collection of quadrics such that when we multiply we get 0. So it's a collection of quadrics which have relations, which is a sort of natural, because this is the it's just a transposition of this this fact that the syzygy is a relation among quadrics. So it's a bunch of quadrics with a relation. It depends on how you want to. And this is the idea in general for defining syzygy schemes. So that's the second part.
Could you explain one more time why there is L1, L2, L3? That seems quite important. So this is exact. So
yes. Okay. So
P is x1, x2, x3.
So we actually out of this sequence we get antisymmetric. What is so we get an antisymmetric, skew symmetric matrix 4 by 4. So a skew symmetric matrix will correspond to an alternate form. This will be here. Okay, I have to write it down. Yes, it's not completely obvious, but it's doable. We have to write down exactness of. We have to write down delta of alpha to write down this alpha explicitly, and we will see that there are some linear forms involved in alpha, and these Q's, if we identify, it will be exactly the minors. But we have to write it down. It's something to. But we can do it after. Okay. So now, how are syzygy schemes defined? And I will take this opportunity just to advertise a little bit this subject, because it's a completely open. There are very few things which are known in this area. So how are they defined? The syzygy schemes are defined in a similar way. So the idea is the following: if we have a non-zero Betti number on the linear strand, which means we have something in here, in Kp1, then this Kp1 is isomorphic to the kernel of this map, which would mean a bunch of quadrics with some relations. And we just take the scheme defined by these quadrics. cut out by this quadrix. And this is the syzygy scheme. But let's write it down. Let's write down the general definition. So I should give credit to Mark Green. It's not the paper from Journal of Differential Geometry 84. It's a paper in Duke before that, 78 or 80s. So it's a paper which is not that well known. But in the first paper, this paper, there's the first account of syzygy schemes. Then Schreier and his students, Bauer and Hans Christian von Bottler. So they all four contributed to this subject. And yeah, it stops somehow here. So I should be very happy to add some more names on the list. Okay. So with the usual notation, we take alpha, non-zero element in wedge P of V, tensor V. So remark that for the time being, there is no variety in the picture. So we just take one element in this space. Then delta of alpha is an element in wedge P minus 1V tensor S2V. So delta is the causal differential for the projective space. So delta of alpha will be a sum over the length of I. This is a multi-index xi tensor qi. So this is the usual notation. X of the so xi is xi0 xi p minus 2 . Then we get a bunch of quadrics. So we get these QIs, this collection of quadrics. And the scheme defined by these quadrics is called the syzygy scheme of this element alpha, and is denoted by SIDS alpha. So these schemes are always cut by quadrics. I would like to keep this a little longer, so maybe I erase here, and after the talk we discuss this. Okay. Another way, so independent of the choice of coordinates, we can delta of alpha can be seen as a map from wedge P minus 1 V dual to S2 of V. And we get the ideal generated by so this is a linear map. It will have an image here, which is the span of these quadrics. And the ideal of, so the syzygy variety is defined by the ideal generated by this, the image. So the image generates an ideal which gives the syzygy scheme. Now let's make some remarks. So first, by definition, since this variety Z or the scheme is defined by the quadrics Q, this quadrics, any quadric will vanish along Z, and this means that alpha becomes a Koszul cohomology class for Z. It defines a Koszul cohomology class. Defines, not becomes. Defines. So this will define a class in KP1 of Z. And we can see, so this alpha at the beginning is given in an abstract way, without a variety. If we want to emphasize a variety for which alpha is a Koszul cohomology class, then this is the largest variety or scheme. So in other words, this is SID of alpha is the largest variety such that alpha is defines a syzygy. And then another remark is that just by definition, if we modify alpha by something coming from wedge P plus 1 of V, the syzygy variety is the same. Because if we modify by something which comes from wedge P plus 1 of V, when we apply delta, it will cancel. So it doesn't have any effect on Q. So SIDS of alpha only depends on the class wedge P of V, tensor V, mod out wedge P plus 1 of V. And another remark, but this is a theorem. Green. The number of independent quadrics QIs is at least P plus 1 choose 2. So we'll always have at least this number of quadrics.
Is less than or bigger than?
It's bigger. Is at least.
The number of independent quadric is bigger than P, bigger than?
Yes. So it's never lower. So this space of quadrics tends to be quite large. Okay.
Twist cubic is CC of what? What kind of element?
Sorry?
Twist cubic is CC of some element?
Yes, I will come to in just 1 second. Because I will just give these examples and then I will stop. And tomorrow I will discuss more examples and classification of these syzygy varieties. What we know so far and what will we expect in general for these syzygy varieties. So just another remark, and then I go to examples, and then we go for a beer. So if X is in Pn, and alpha is in KP1 of X, then X is contained in seeds of alpha. What does it mean that alpha is KP1 of X? It means that delta of alpha will vanish along X. So the quadrics QIs will vanish along X. So these quadrics, the fact that alpha is in KP1 of X means that these quadrics are in the ideal of X. It is the same. So you see, if
What PP is any number?
any number bigger than 1, at least. For 1, it's not that interesting because we get just the quadrics in the ideal. At least 2. Yeah, just to make sense.
So it seems 2, 3 equal not 0 and make something this process.
Yes, yeah, that's somehow the idea. If
2, 3 is not 0, so
this is the philosophy of Schreier, or the approach, one of the possible approaches, which is finer than what we have so far in Green's conjecture or other type of similar statements. So we want to prove that this guy vanishes in some setup. Suppose it doesn't, then the variety will be embedded in some syzygy variety. And then we try to classify these varieties and say that this is not possible in the... So our variety cannot lie on this type of variety.
So it's vanishes.
Yeah. So actually I will anticipate a bit, and I would say that these varieties tend to be of very small degree, very close to minimal degree. We will see tomorrow in the classification that in some cases there are varieties of minimal degree or one more than the minimal degree.
So X is minimal degree, then what is this alpha?
Okay, let's see some examples. Let's see twisted cubic. So twisted cubic. I just repeat now the Betti table. These are the 3 quadrics. These are the 2 relations in the ideal. So we have Q1, Q2, Q3, the quadrics which generate the ideal. And we have 3 relations. So these quadrics are the 2x2 minors of the matrix x1, x2, x0, x1, x2, x1, x2, x3. So the 2x2 minors of the matrix. And then the relations are just given by the 2 rows. And suppose we have alpha different from 0, an element in K21 of C. So this is C in P3. This means that we choose one of the 2 relations. So let's choose, or we can choose any relation. So we have one relation, L1 Q1 plus L2 Q2 plus L3 Q3 equals 0. Where L1, L2, L3 is a combination of these. And then the syzygy variety of this alpha coincides with C. And why is that? Because L1, L2, L3 will be a combination of, so if we write L1, L2, L3 as a row, this row is a combination of this row and this row. If we apply delta, so this the new quadrics which appear out of this alpha will be or will be combinations of these three quadrics. So we will get three possibly new quadrics, but again will be independent. So they have to generate the same ideal. And these quadrics will be in the ideal of the twisted cubic. So this is the only possibility. This generalizes to rational normal curves. So let me just, and this is the last. Let me before going to rational normal curves, let me just point out that we had 7 points in P3 and alpha in K21 different from 0. Then the syzygy variety of alpha was a twisted cubic. Okay, and the last example, and I will stop here after that. So if C in Pn is a rational normal curve, then the minimal resolution is the following. So starting from the tail, we have n-1 copies of S of minus n, 2 n choose 3 copies of S of minus 3, n choose 2 copies of S of minus 2. And these are the quadrics which generate the ideal. So again, a rational normal curve is given by the 2 by 2 minors of the matrix. So these are the quadrics which generate the ideal, and then there is a way to build a complex out of that. And if we take alpha different from 0 in k n-1, 1 of C, which would be which would correspond to the last part of the resolution, then by this remark by Green, the number of quadrics involved in alpha is at least n choose 2. So the number of independent quadrics in delta of alpha is at least n choose 2. And these are quadrics in the ideal of C. But on the other hand, the ideal is generated by n choose 2 quadrics. So they should be the same. Yes. So the syzygy variety equal to C.
Is there any example which syzygies variety give more information on C? So
yes, of course, yeah.
If
we will discuss
this
tomorrow.
n-1, then it is some minimal surface.
If you take here,
n minus 2, 1. Yeah.
good question. I don't know.
So CG alpha.
I don't know. I don't know the answer. If we take alpha not here but in k n minus 2, 1.
Yeah, n minus 2.
I don't know. Could be a surface. Let me see. Yes, the answer is either C or a surface of.
But K21 in this case, K21. If we take K21 alpha, then.
Yeah, but the interest is look in this kind of questions to look at the tail rather than at the beginning. So yeah, the answer.
K21 is quite another maybe gives some idea.
Yeah, this is also interesting, K21. But probably not too interested if you can prove that B13, if there are no cubics, then K21 is already determined by the Hilbert function. So yes. Okay, so the answer here is, so it depends on the class. So it's either C, can be C again, or a surface of minimal degree. But this is a part of a theorem, which we'll discuss tomorrow. So it's not completely obvious. But if you ask me,
on the class.
Yeah, it depends on the class.
So
It will depend on what I will call tomorrow, and this is a notion introduced by von Bottmer. It depends on the rank of the class. So yeah, the rank. There is a kind of stratification of the classes according to this notion of a rank. So the answer depends on the rank of that class.
That is easy. The last one, K n minus 1 doesn't depend on the class.
This doesn't depend on the class.
It's not depend. It does. It also
No, it doesn't. No, it doesn't.
But the last, so
It doesn't depend on the class.
Why?
Well, because this is life. As I told you, it's a mysterious subject. So there are many things to be clarified, even in
So hard. It used to be hard.
No, it's not that. Yeah, probably it's hard, but I mean, a general approach for any class, it's out of reach for the moment. But if we are very close to the end of the tail, then things can be proved.
After four professors defined this system, right? And is there any followers to keep going on these topics now?
Who define?
She's been trying.
Yeah, you can prove many things. So if you have a classification of, I will tell you tomorrow what's known, and what we could prove if we knew more about this. So the newest one is a paper of von Bottmer from almost 10 years ago. So since then there was basically no progress in the yeah.
In your opinion, is the topic good?
Sure.
Generation like these guys.
Of course, yeah, definitely, yes, because these are very interesting varieties.
Yeah, so how? What is some problem to keep going for the research? So, for example, techniques are not so good, or
well, the techniques are not so good actually. Yeah, this is one problem. And so the only technique which was used so far was projection of syzygies and hyperplane sections.
Yes.
This is the only thing we used.
Yeah,
Yes.
I like projections.
Well, I will take at least 20 minutes tomorrow to talk about projection of syzygies.
Yeah.
Because these syzygy varieties are related directly to projection of syzygies.
Yeah.
They
And it is good for our groups.
yes, can be. It's an equivalent condition. So it's strictly related to projection of syzygies.
Yeah.
I need beer.
Thank you.